Welcome. In this video, we're going to discuss another crypto system called linear codes. In a previous video, we looked at the generalized Caesar's code where we shifted by a k value. In this video, we're going to extend upon that idea. We're not just going to shift by k, we're also going to scale our letter in the alphabet by multiplying it by a. So this is the encoding function that we're going to use. Let's try to think about inverting that encoding function, because remember, every encoding function has to have a corresponding decoding function, so we'd like to invert this. So taking an inverse, you would write e of x as x and make that congruent to a y plus k. So what we have to do is solve for y. The first thing that we're going to do is subtract k on both sides. So we get x minus k is congruent to a y. And then finally, we would like to move the a to the other side. So the way that we would do that in mod 26 is multiply both sides by the inverse of a. So a inverse gets multiplied on both sides to give us a inverse multiplied by x minus k, which is congruent to y. So this expression here represents the decoding function. Now notice, in order to go through this process of this step right here to this step, we need to make sure that this inverse exists. Let's remember, sometimes the inverse doesn't exist at all. But here it will exist when we're relatively prime with the mod. So a being relatively prime with 26 is an important condition when we're building a proper encoding function with the linear code. So the receiver plugs things into the decoding function to decode what the sender has sent away. Now it is possible to attack the linear code as well. It's a little bit more challenging than the Caesar's code that we looked at before, but there are some strategies that the kibitzer could use, and these strategies could be done by hand. Of course, it speeds things up with the computer, but you don't necessarily need it. So the first thing that the kibitzer could do is say, oh, well, in the English language, there's a frequency analysis. Some letters appear more often than others. In fact, the letter E appears most often. 12% of the letters in regular English come out as the letter E. T is the second most common at 9%, and then all the way down to Z is the least common at like 0.07%. So if you want to try to write something in English and you don't follow this regular frequency, it comes out as a really weird sentence or paragraph. And people have tried doing this, and it's kind of a funny challenge to avoid these frequencies. So it is possible, but it certainly doesn't sound natural. So what the kibitzer could do is say, hey, the letter R, for example, is appearing a lot during this ciphertext. So they say, oh, R is maybe E, as a fairly educated guess. So they could do that type of thing to get them started. So another thing that the kibitzer might be able to do is some kind of educated guess, trial and error type of thing, to say, oh, this letter is appearing all by itself, and letters that appear all by itself are commonly like the letter I or the letter A. Or they might find, oh, these three letters commonly appear together, so that might be the word like the or and or something like that. So they could try something along those lines. The third option that the kibitzer might be able to deal with in attacking the linear code is if maybe through the first two options they find out two letters. If they find out how to decode two of the letters, what they could do is set up a linear system. So a possible linear system is set up below here, and notice that there's two congruences and two variables, b and c. So you could solve for b and c. Note that you're given that x1 decodes to x2 and y1 decodes to y2. So you have those numbers. If you could just figure out the b and the c, then you have the whole decoding function. So let's give this a try on the next page in terms of playing the role of the sender, the receiver, and the kibitzer. So first, the sender wants to send away the word this. So let's set up the encoding function. Okay, so we're going to be encoding each one of these letters, and we're given that the A value is 5, so I'll write 5, and then an open bracket and close bracket for whatever T is, and then the K value here is also 5, so I'll write 5 for that. And T, if we look up on our table for how to convert letters to remainders in mod 26, T is 19, so I'm going to write 19 there. And we're going to do the same thing for H, I, and S. So H is 7, I is 8, and S is 18. So you might want to pause the video for a moment now, practice your modular arithmetic, and reduce all of these expressions in mod 26 to find out what the sender would send away as the gibberish or the ciphertext. So go ahead and give that a try. I'll put the answer on the screen in 5 seconds. So we ended up getting 22 for W, 14 for O, 19 for T, and 17 for R. So the sender would send away water. Okay, so now we're ready to do some decoding. Let's play the role of the receiver and decode LTII. So let's remember back to previously in this video we discussed the inverse to the encoding function, which was A inverse multiplied by x minus k. So the question is here, what is our A inverse? Well, our A is congruent to 5. So if we try to think of A inverse to correspond to that, maybe we'll try to think of multiplying by 5. So 5 times 5 is 25, and that's -1. So the inverse you could write as -5 if you like. You could also write it as 21. So when we write our decoding value for L, we would write that this is congruent to -5 multiplied by L, which is 11, minus 5, minus the K value. And we'll repeat this for the other letters. Notice that we don't need to repeat decoding I. It's the same calculation. We just have to do that once. So go ahead and give this a practice now. Pause the video and see if you can reduce these to their remainders in mod 26. I'll give you a few seconds. So this time we get 22, which is W, 8, which is I, 11, which is L, and there's 2 of them. So the word that we're finding out here all along is the word will. So finally, we'll play the role of the kibitzer. So the kibitzer has been looking at CFRR and is trying to decode that. The kibitzer has taken this from a long passage of ciphertext, and there's some frequency analysis going on here. The Z appeared most often, while the letter W appeared the second most often. So according to the table that we looked at earlier in the video, Z, a good guess for Z would be that it's the letter E. A good guess for W would be that it would decode to the letter T. Let's write that down. So this gives us a good start at trying to do the decoding of CFRR. So what the kibitzer would do here is say, okay, I'll let the decoding function be. It's just some linear function that they are going to try to find. they're going to let it be bx plus c. And we'll try to figure out what the b is and what the c is. And what we can do is plug in z. If we plug in z, let's write z as -1, and multiply that by b and add c to it. What it's supposed to decode to is e. So we'll write e as 4. And we also know about w and t, this similar sort of thing. If we plug in w, which is -4, multiply that by b, and add c to it, we're supposed to get t, 19, or maybe -7. So we'll write -7. Remember, all these congruences are in mod 26. So with the congruences that we put on the screen now, they're very similar. What we could do is subtract them and get rid of the c, and see what happens on both sides of this congruence. So 4 minus a -7 would give us 11. On the right-hand side, the c's would cancel out for us, so that's nice. And then for b, we have minus b minus a -4b, so we have 3b left. So to solve for b, we will multiply both sides by the inverse of 3, which is 9. So b is congruent to 9 times 11. And that reduces to -5. So our b value is -5. Now that we have our b value, we can go ahead and plug it back into the b from above and then solve for c. That will give us our c value. So our c value would be, looking at the first equation right here, if we plug in b as -5, we would get 5 right here. So our c value would be -1, because we would take 5 minus 1 to give us 4. Now we have a b value and a c value. So we have the whole decoding function, and we can go ahead and do the decoding as we did above, but with this corresponding b value and c value that we just found. So let's write down the decoding. So if you'd like to give this a try, let's remember that all of these calculations that we're doing are in mod 26. Notice that we've plugged in our b value as -5 and our c value as -1, and the letters c, f, and r right there. So go ahead and pause now if you want to give that a try, and I'll reveal the answer in just a moment. So what you should decode that to is the word pass. We knew the last two letters were the same because it was RR. So there's a theme going on here with quotes. So the quote that this sender, receiver, kibitzer, we're all intercepting different parts of is, if we zoom out, the quote is, like everything else in life, this will pass. Thanks so much for listening, and we'll see you on the next one.